Okay. So, hello to everyone. So to people online, if you don't hear us, just write or send the comments or just speak.
Don't hear us, they won't.
Yeah. Yeah, that's true. Yeah. I mean, if they can barely hear. So today we have Theo Jacobson from University of Minnesota. And, he's a PhD student there, so will graduate soon. And it's gonna talk about the one-form symmetries versus large N QCD. Welcome here.
Thank you. All right, thanks for the introduction. Thanks for the invitation. I had a nice drive down from Minneapolis last night, and I'm happy to be here. So yeah, I'm going to talk about some work with Alexei Cherman, my advisor, and Maria Nugel, who's another graduate student at Minnesota. And it's about sort of tension between one-form symmetry, something called one-form symmetry, and confinement in large NQCD. And feel free to just interrupt me with questions. Yeah, I think I want to spend some time introducing this concept, which might be new to some of you. So just, yeah, interrupt. Right, so yeah, as I said, the talk is about a sort of tension between two facts about gauge theories and confinement. So one is that quarks are confined in large NQCD, and the other is that we're now taught that confinement should be associated with something called one-form symmetry. In particular, when these one-form symmetries are not spontaneously broken. Okay, so just to give an outline, I'll just talk about confinement in Pure-Yang-Mills, where it's sort of familiar, the connection to generalized symmetries, and in particular one-form symmetries. Then I'll try to convince you that large NQCD is a confining theory. And nevertheless, there's no one-form symmetry in large NQCD. So there's some obstructions, and I'll discuss them in sort of generality and then consider a simple example to sort of go into it in a bit more detail. Okay, so Pure-Yang-Mills. This is a confining theory. So what this means is if you put in a test quark and an anti-quark, they will experience an asymptotically linear confining potential. And you might ask, how do we know this? If we could, solve the theory, then we would just compute these expectation values, and they would tell us that it's a confining theory. So we compute expectation values of line operators. So the classic indicator of confinement is the Wilson loop. So we choose some closed contour, and we integrate the gauge field on it, do some path ordering, and we take a trace so that this is a gauge invariant quantity, and we take the expectation value. And if for large loops, this Wilson loop falls off with an area law, then this is indicating confinement. So sigma, the coefficient of the area law fall off, is just the string tension. And so we have a linear potential. Okay, alternatively, we can compute the expectation value of something called a Polyakov loop, which is just a Wilson loop, which is wrapped around some non-contractible cycle in space-time. So maybe we're at finite temperature, and this circle is compacted by time direction. Beta would be the inverse temperature. For sufficiently low temperatures, the expectation value of the Polyakov loop is just 0. Okay, that's telling us that the free energy of a single quark, which propagates a single static quark, that free energy is infinite. Okay, so that's confined. Okay, now it turns out that these two line operators are really order parameters for a symmetry, and this was really known since the early days, where it was called center symmetry. And back then, people thought that this was some symmetry which really just acted on Polyakov loops, the topologically sort of non-trivial loops. But more recently, this was identified as just one aspect of something called one-form symmetry, which really acts on all Wilson loops in the theory. Okay. And the fact that this symmetry is not spontaneously broken means that the order parameters have vanishing vacuum expectation values. Okay, so for the Polyakov loop, that's straightforward. It just says 0 expectation value. For the Wilson loop, we have area law fall off, and that means that if we take the size of the contour to infinity, we get 0. Okay, so these should be interpreted as selection rules for this symmetry, and it's an example of a higher form symmetry. What is it? So that's I'll go into much more detail about what exactly it is. Yeah. in a sense, yeah, that's what the talk is about. So roughly speaking, these higher form symmetries, these are symmetries which act on extended operators, not just local operators. So in this case, we're talking about lines, so it's a one form symmetry.
Is P of C exactly 0?
P of C is exactly 0 at
Okay.
low enough temperatures. At very high temperatures, this symmetry is spontaneously broken,
yeah.
and we'd have a non-zero
Okay.
depth. But we're talking about large, yeah, large circles. Okay, so I just want to warm up to the higher form case by considering this sort of, I guess, more modern perspective on just ordinary symmetries, which in this language are zero form symmetries.
Just a second.
Yeah.
So P of C is 0 when you take P equals 0, right? 0 to
Well, in the limit, I mean, you need a non-contractible cycle to wrap.
yes.
I mean, you could think of, okay, on R4, you just send the Polyakov loop from minus infinity to plus
that's what I
infinity.
was thinking. Okay.
Yeah, that's fine. Yeah. Okay, so let's warm up with a zero form symmetry. Suppose we have just a continuous symmetry, a U1 for simplicity. We have a conserved current, and we can use that conserved current to construct a charge operator. Okay, so we take the zeroth component, we just integrate it on space. Here I'm just doing 2+1 dimensions to draw pictures. And this gives us some operator, which is time independent because the symmetry, this current is conserved. So that means that I can integrate on some spatial slice, but if I move it up in time, I get the same answer unless I pass through a charge local operator. Okay, so phi sub q is just an operator which has charge little q under this U1 symmetry, and if I move it past, then I pick up a phase which just tells me the charge. Okay. So one thing that we can do is first integrate on some other surface, which is not just this constant time slice. Okay, nothing stops us from integrating, the analogous quantity, but just on some other surface. And then the fact that this symmetry is a symmetry and the current is conserved means that we can deform the surface freely, and it doesn't change the answer unless we move it through some charge operator, in which case we get a phase. And so people say these charge operators are topological operators, and they're supported in this case on surfaces. And yeah, so this is the modern point of view, is that a symmetry is just the existence of topological operators of this type. And it just shortcuts the need for a conserved current. So in particular, this works equally well for discrete symmetries. And it allows for many generalizations of the notion of symmetry. So let's just see in a bit more detail how these topological operators show up in the case of discrete symmetries. So this is, I think, easiest to see on the lattice. So let's just consider this sort of toy model. Phi is just a real scalar field at each lattice site. Okay, we have the lattice derivative, and this has O2 symmetry, but we can just look at the Z2, which just flips the sign of phi. Okay, if we flip the sign of phi at each site on the entire lattice, that leaves the action invariant. Okay, but if we only replace phi by minus phi within some region, then we get something interesting. So these red dots are the sites where I flip the sign of phi. And everywhere in the region, the action looks the same. Everywhere outside the region, the action is also left invariant. But we only pick up something non-trivial right at the boundary where one site picked up a minus sign and the other didn't. Okay, so that flips this minus sign to a plus. And so we can view this, the boundary of this region, as some kind of defect, right? It modifies the action for all links which are crossed by this line. And it's a topological defect because if we start flipping signs of these scalars near the boundary, it will move exactly where this defect is changing our action. So we just do these field redefinitions and we move where this boundary is. So this is one of these symmetry operators.
What did you do to go from these different?
Yeah, so if I flip the sign of this site,
Yes.
then it will cancel the modification here, here, but it will introduce one here and here.
Okay.
So it moves the line over.
Okay. Okay.
And then similarly, if I flip this sign, it'll move the boundary.
Right. Yeah. So you're just saying, showing how flipping the sign moves the boundary.
Yeah.
Okay.
Yep. And if this, if we added some term in the potential which did not was not invariant under the Z2, then we would not be able to do these manipulations, and these lines would not be topological defects. They could, we could still define them as defects, as modifications of the action, but we couldn't move them around. Okay, so I sort of tried to arrive at this defect by doing something in some region and looking at its boundary, but we can also just construct them on any line which maybe isn't the boundary of some region. And so that's this U of gamma. And if we move this line past some operator phi living on a site, then we pick up a minus sign. So that implements the symmetry transformation. So that's the zero form case. Now we want to generalize this to one form symmetry and then to higher form symmetry. So for one form symmetry, we want something that acts on line operators rather than local point-like operators. So before we had some surface in 3 dimensions, which is sort of enclosing a point. Now we want some operator which is going to enclose a line. So we have to go down 1 dimension to this curve in 3 dimensions. Okay. In general dimensions, we are looking now at codimension 2 topological operators. So in 2 dimensions, these are point-like local operators. They're lines in 3 dimensions, and they're surfaces in 4 dimensions. And if these one-form symmetries are continuous, then they just are described by a conserved 2-form current. So J mu nu is some anti-symmetric tensor, and it's conserved. And the operators which are supported on these codimension 2 manifolds would just be the integral of epsilon j on the appropriate manifold. But again, this perspective that we just have the topological operator, that works also for discrete symmetries. Okay. And in general, for a p-form symmetry, we associate that with codimension p plus 1 topological operators. So it just sort of generalizes easily. So that's a one-form symmetry. And the simplest example is probably in Maxwell theory. So we just have f squared, that's our Lagrangian. So from the equations of motion and the Bianchi identity, we actually get 2 different conserved 2-form currents. One is just the field strength, and the other is its dual. Okay, so in the absence of sources, both of these antisymmetric 2 forms are conserved, and they give rise to the so-called electric and magnetic U1 one-form symmetries. Okay, now the reason these symmetries exist in pure Maxwell theory is just because electric field lines and magnetic field lines can't end except if you put in a source, some static source. Okay, so the fact that we have these higher form symmetries and these topological operators is basically a fancy way of saying you have like Gauss's law, right? When you teach Gauss's law, you say you can use any Gaussian surface you want, you can manipulate it and whatever, but you always get the same answer for the charge inside because field lines can't end. Okay, and in quantum field theory, the operators which are charged under this symmetries are Wilson lines and 't Hooft lines. The Wilson lines represent closed world lines of electric charges. 't Hooft lines are closed world lines of magnetic charges. They create some field, and that field can't be screened, and so we have this symmetry. But the symmetry can be broken just by adding sources, dynamical charges, electric and magnetic. So if we have some source, then the right-hand side of these equations are no longer 0, and the symmetry is no longer there. And since charges are quantized in U1 gauge theory, we could ask, if we have charge n electric matter, how does that break our symmetry? Well, it breaks it just down to Zn. So that's saying that flux lines can end in multiples of n, where you have some dynamical charge, which is screening. Okay, so back to Yang-Mills theory. Again, probe quarks are confined by flux tubes, and we can take the fact that there is a stable flux tube to say, there should be some symmetry associated with that. Okay, so there should exist some operators which measure the charges of Wilson lines, but only modulo screening by dynamical charges in the theory, which are gluons, which are in the adjoint representation. So this is a one-form symmetry. These operators are supported on codimension 2 manifolds, and they can only detect the charge of a Wilson line modulo the adjoint representation, And so that information is carried by the anality of the representation. So that's the charge of the representation under the center of the gauge group. And that charge takes values between 0 and n-1. So yeah, it's a mod n charge. And as a result, the symmetry is just a Zn symmetry. And we denote the symmetry generators of those topological operators by U sub k. K is a label which labels the group element in Zn. And MD-2 is the D-2 dimensional manifold on which this operator is supported. And sometimes people call these operators Gukov-Witten operators. On the lattice, they have a much more concrete definition, and they're sometimes called center vortices. And we'll see an example of that definition later on in the talk. Okay, but these operators exist in SUN Yang-Mills theory. Okay, so the fact that they're topological means, again, we can just deform them freely in a correlation function and we don't change the answer. The fact that they're associated with a Zn group means that if we take two operators and we put them close by and fuse them to the same codimension 2 manifold, they fuse according to Zn group multiplication. So you take the K and the L lines and you fuse them, you get the K plus L line mod n. And then most importantly, they have an action on Wilson lines. If you surround a Wilson line with one of these topological operators and you shrink it on the line, you pick up a Zn phase, which tells you the anality n sub r of the Wilson line. So just for fun, I want to show how one can arrive at selection rules just by using these topological operators, just by manipulating them using these rules. So I'm getting kind of far from the computer, but so let's start with the Polyakov loop. So here I'm taking like a periodic box for my spacetime. I have a Polyakov loop, and we can insert the identity in the form of one of these topological operators and its inverse. Okay, they're lines.
So here you have anti-periodic boundary condition?
Periodic.
Periodic.
Yeah, just the pure gauge theory. So.
Oh yeah, okay,
Yeah.
okay, yes.
Yeah. So I insert two of these lines, insert the identity in the form of UK under UK. I move one of them past the Polyakov loop, and I get this Zn phase, which measures anality. Here I'm just taking the fundamental rep for simplicity. Okay, and then I can move this topological operator using periodic boundary conditions onto the left, annihilate them, and the thing I'm left with is just the same Polyakov loop expectation value I started with, but times a phase, and that equation only holds if the expectation value is 0. So this is just like the standard sort of quantum mechanics way of deriving selection rules, but hopefully showing that we can use these operators and topological manipulations to arrive at the same type of thing.
So there are examples where you can use selection rules from the one-form symmetry concept that could not be argued from any other perspective before.
Let me think about that. Yeah, I think that's right. I mean, by the time you've done suppose you didn't know about the concept of one-form symmetry, and you had some argument that a line operator expectation value was 0, roughly the same amount of work would be required to say that you have the one-form symmetry, at which point all the selection rules sort of follow.
Okay.
Yeah, there are some sort of more exotic examples with non-group-like symmetries where there are non-obvious selection rules, I think, but yeah. Okay, so that was just a sort of fun exercise, but there are other reasons why these symmetries are useful. In particular, they, just like ordinary zero-form symmetries, they constrain the dynamics and possible phases of quantum field theories. So not only can we use them to derive exact selection rules, they're also just part of the non-perturbative definition of the theory, unlike the gauge group, which might be different depending on what duality frame you work in. These symmetries are there at weak coupling, at strong coupling. They're invariant under RG flows, and they can be involved in 't Hooft anomalies, which are just obstructions to gauging the symmetries. So there's a notion also of gauging these higher form symmetries. And these give rise to pretty powerful constraints on phase structures of gauge theories that otherwise this would be absent. Okay, but they also give new perspectives on sort of known physics, new language to talk about things like confinement, which is the subject of today's talk, and also this new sort of formulation has led to some kind of generalized Landau paradigm, where we can not only label phases of matter by whether ordinary symmetries are spontaneously broken or not, but also higher form symmetries. So this is sort of now the standard way of talking about things like topological order and other topological phases of matter. We have Goldstone theorems associated with these generalized symmetries, et cetera. So there are many, many applications, and they've really proven to be very useful. But nonetheless, today's talk is sort of about maybe some limitations of one-form symmetries, or at least situations where there's a disconnect between this useful notion and something it's supposed to be related to, namely confinement. Okay. So one-form symmetries are useful, but unfortunately QCD itself has no one-form symmetry. So just like Maxwell theory had electric and magnetic symmetries, which were broken by dynamical matter, in real world QCD with fundamental quarks, we don't have a one-form symmetry, and the reason is just that confining strings can break due to pair production of dynamical particles. So the effects on Wilson loops are just that you get perimeter law rather than area law. So roughly, the Wilson loop expectation value becomes a sum of two terms, and for sufficiently large contours, the perimeter term goes to zero slower than area, and so you pick up that contribution, and you can actually renormalize that perimeter contribution away, and so the Wilson loop has a non-vanishing vacuum expectation value, and similarly, the Polyakov loop becomes non-zero. So that's for Wilson loops. Those are the would-be charged operators under the symmetry. And then we have also an effect on the symmetry operators. They just fail to be topological. So they still exist, but you can't freely deform them, and they don't generate a symmetry. It's broken. Okay. But one might hope that there could be something in large N QCD. So of course, QCD has this hidden parameter, which is 1 over n. And we can consider an 't Hooft large N limit where we take n to infinity, but keep the strong scale fixed. And let's say, I think for the whole remainder of the talk, I'll just be taking like a single flavor of quark, fundamental quarks. And the key features of the 't Hooft large N limit are, one, that gluonic observables don't see quarks at leading order. So quark loops are suppressed, and that means that a generic gluonic correlator in large N QCD will just be equal to its Yang-Mills value plus 1 over n corrections. And secondly, that the large N limit is a sort of classical limit where nice, well-behaved observables operators factorize up to 1 over n corrections. Okay. So because of these two properties, large N QCD is really a confining theory. So if you compute at large N the Wilson loop expectation value, it has area law, and similarly, the Polyakov loop expectation value vanishes at large N. Okay. So this is all up to 1 over n corrections, but the point is just that screening, which is what screening is the reason why you don't have a linear potential in real QCD. Screening is 1 over n suppressed, and consequently, large N QCD has exactly the same selection rules as pure Yang-Mills if we just look at these line operators. And so the question is, does it have the same symmetries? Is there a one-form symmetry in large N QCD? So certainly the expectation is that there exist some operators which we can define in QCD, which they're not exactly topological, but they are topological in the large N limit. Okay? They're topological up to 1 over n corrections. But it turns out that that expectation is just false, and there are certain obstructions for this scenario to be realized. So one is the existence of open Wilson lines, okay, the fact that large N QCD has non-trivial open Wilson lines, and the other is that precisely for these operators, which would have generated the symmetry, this usual large N counting that quark loops are suppressed just breaks down.
Do you have a picture of that?
Of
Why
the,
it breaks down?
yeah, I do,
Okay.
yes. Yeah, so I'll talk about these two aspects and then in sort of in general, and then look at this two-dimensional example. Okay, so it turns out that higher form symmetries are broken when the charged operators, like Wilson lines, are endable. Okay, so this is basically equivalent to saying that the, like in Maxwell theory, introducing dynamical sources breaks the symmetry. You have a new set of operators when you have dynamical particles. So in QCD, Wilson lines are endable in the sense that you can consider an open line. So you take a dynamical, Q here is the dynamical quark. You have Q bar at X, Q at Y. You string a Wilson line between them. That's a gauge invariant operator in QCD. Okay, and I've normalized it so that it has a nice large N limit. So why does this cause a problem for the symmetry? So let's just suppose, for the sake of argument, that there exists some codimension 2 operator which is topological. Okay, and let's just assume everything I'm about to do holds in the strict large N limit, so up to 1/n corrections. So what we can do is we take our open Wilson line and we sort of lasso this would-be topological operator around it. And then we can shrink it in two different ways. So one way is to just shrink the line on the open Wilson line. And then by assumption, this operator is generating our symmetry. And when we shrink it, it picks up the Zn phase measuring the charge of the Wilson line. On the other hand, we can move this topological line over the endpoint of the open line and shrink it somewhere very far away, in which case we don't get a phase. And either one of these choices is supposed to be valid. And so if we compare the end results on both sides, we'd have to conclude that this open Wilson line is equal to itself times a phase, which means it's 0. Okay, so this, again, this would be consistent if the open Wilson line expectation value vanished at large N, so it was order 1/n. But in reality, when properly normalized, these open Wilson line expectation values are order 1, and they will also have order 1 correlation function. So this is really a non-trivial operator. So that means that our assumption that this topological operator with these properties exists was just wrong. So this is a very slick argument that basically just rules out, it doesn't require us to make any choice for like a candidate operator that is going to become topological at large N. It just says such an operator can exist.
Yeah, so even though there is a notion of center symmetry, this notion doesn't hold, right?
That's right. So one has to really sort of dig into, carefully dig into what one means by center symmetry. But this rules out the standard definition of one-form symmetry is ruled out by this argument. Okay. So this is a nice slick argument, but it also doesn't really make contact with the whole reason why we expect that there might be a symmetry at large N, which is just that quark loop effects are 1/n suppressed.
So this is you also played with the Veneziano limit.
Oh, we did not. Yeah. So I think in that, well, it depends what you mean, but in that limit, one would not expect any emergent symmetry. If you look at Wilson loop expectation values, they're not, or probably like the selection rules aren't quite there in the Veneziano limit. Yeah. Okay. So the second sort of obstruction is the failure of quark loop suppression. So again, the standard large N lore is that a gluonic observable in QCD, large N QCD, has its Yang-Mills value plus 1/n corrections. So let's examine that in more detail. So first we have to ask, what are the interesting operators that we want to ask about at large N? So we have Wilson loops and we have symmetry operators. So which are the interesting Wilson loops? At large N, the interesting Wilson loops are those with representations which are contained in a finite tensor product of fundamental and anti-fundamental. So That includes like fundamental representation, anti-fundamental, two-index representations, adjoint, etc., but nothing that scales with n. And that ensures essentially that these operators just have non-vanishing expectation values and correlators. So they survive the large n limit. But once we say that, we are actually restricted in the class of interesting symmetry operators. Okay. It turns out that we have to take the label k, which labels the group element, to be order n. So k cannot be order 1, it can't be order root n, it actually has to be order n. This ensures that the operator u sub k will actually act non-trivially on the set of interesting Wilson loops. So this topological operator will act on the Wilson loop in representation R by multiplying it by some phase. But we said that the anality has to be order 1 for this Wilson loop to survive the large n limit. But if the anality is order 1, then k needs to be order n in order for this phase to be non-trivial at large n. So as a result, we have to say, for there to be a non-trivial one-form symmetry, Zn one-form symmetry, the u sub k's with k of order n have to be topological. So it would somehow not be enough if u sub 1 were topological, because it's essentially the trivial operator at large n.
Okay, I'm a little bit confused. Didn't you argue in the previous slide that there are no topological operators?
Yes, but there's a loophole if this phase is actually negligible at large n.
Okay.
Right. I mean, if k is equal to 1 and you take the large n limit, then this phase just disappears, and this is not really a constraint.
Right.
But it also means that the operator didn't do anything.
Right.
It didn't act at all, so it's just the trivial operator.
Right.
So that's fine. Okay, so we should look, when we look at expectation values, we want to look at these symmetry operators with k of order n. Those are the interesting ones. Okay, and it turns out that the correlation functions are really just the expectation values of symmetry operators are highly constraining, and this allows us already to rule out or to see this quark loop non-suppression. We can just look at the expectation values. So if we had an exact Zn symmetry, then the expectation value of u sub k we could write as the expectation value of u1 to the power k, so k copies of the u1 operator. That's just using the fusion rule. And then we could factorize that expectation value because these operators are topological. So okay, so that means that the expectation value of u sub k is a kth root. Is a root of unity. And in particular, if it's defined on a contractible manifold, which you can just shrink to 0 size, the expectation values are just exactly 1. So this is a very tight constraint from an exact, what we would have from an exact symmetry. So in large N QCD, it would be natural to expect that this U1 operator, which is almost trivial at large N, its expectation value is the pure Yang-Mills answer plus 1 over n corrections. And similarly, from like large N factorization, if you take 2 copies of that operator, it will factorize again up to 1 over n corrections. But we don't want to know about U1 and U1 squared. We want to know about U sub k. So if we think of U sub k as k copies of U1, and then start to factorize, the correction to full factorization will be 1 over n for each pair in this collection. But there are k squared pairs. So we expect the correction to factorization to be k squared over n. Okay. So if k is of order n, the correction to factorization is order n. And so this is wildly deviating from the expectation from if we had an exact CN symmetry. So roughly speaking, the reason quark loops are not suppressed is because you can think of these operators as being a large n number of well-behaved operators, and such a large n collection does not have nice large n behavior. Okay. So just to recap, In pure Yang-Mills theory, we know that confinement is associated with this exact one-form symmetry. We have the exact same selection rules in large N QCD as we do in large N Yang-Mills, but there's no symmetry to explain those selection rules. Okay, so these two considerations tell us that there's no emergent, in the sense of emerging in the n equals to infinity limit, no emergent Zn one-form symmetry, which is going to act on Wilson loops. And that's just a statement that these topological operators just don't exist at large N. Okay, so maybe I'll stop for questions right now before I get into the example.
Do you want to elaborate on the idea of emergent center symmetry versus this, and what might be wrong with emergent center symmetry?
Do I want to? Maybe at the end.
Okay. But that's the only thing I can think of right now.
Okay.
But yeah. Okay.
Yeah.
No, that's fine. Go ahead.
Okay. So I just want to work out, in the simplest possible example where you might expect there to be an emergent symmetry at large N, how it sort of fails to arise. And the simplest example we could think of is just 2D QCD with scalar quarks, and we put the theory on the lattice because we can do actual explicit computations of Wilson loops and polygon loops and C screening very concretely. Okay, so this is just the lattice partition function for this scalar QCD. So we have some pure Yang-Mills part of the action, which is a function of plaquettes, U sub p, and then we have the coupling to matter. So this is just the standard hopping term. So phi x is a complex scalar vector in SUN. UL is the SUN link variable, and this is just the on-site mass term for these complex scalars. And in order to actually compute something, we do a hopping expansion. So that means expanding in this parameter kappa, which sits in front of the hopping term. Okay. So in this hopping expansion, you basically bring down a bunch of powers of phi dagger u phi, and then you integrate out the scalars with this Gaussian weight. Okay, and in this expansion, a generic gluonic observable is expressed as a series. So the first term in the series is just the Yang-Mills value, and then we have a sum over hopping loops, which are just closed Wilson loops representing the closed world lines of these dynamical scalar particles. They come weighted by kappa over m squared to the length of the loop. And then we have to evaluate this expectation value of our operator with the collection of hopping loops in the pure gauge theory. Okay. So the reason we're working in 2 dimensions in particular is because pure gauge theory is basically completely solvable. And so we can, in principle, compute all of these expectation values. Okay. And the interesting observables we'll look at are, again, Wilson loops and the operators which generate the exact one-form symmetry in the theory where we ignore, completely remove the matter fields. So those are both gluonic operators. And you can see from the structure of this expansion that a small kappa expansion physically is a large mass expansion. So physical quantities depend on this ratio, kappa over m squared. Okay, so just as a warm-up, let's look at the Wilson loop expectation value in pure Yang-Mills in 2 dimensions on R2. So here I'm taking a very large, let's say, periodic torus. So if I put in a Wilson loop in the fundamental representation on some contour, there's a very easy recipe for computing this expectation value. So this separates my R2 spacetime into 2 regions, and then each region just contributes some weight to the expectation value. So the weight has some prefactor which depends on the dimension of the representation which appears in the region, and some weight which depends on the size of the region and the Casimir, the quadratic Casimir representation. So outside we have the trivial representation, there's some prefactor, and then it comes with e to the minus g squared is the gauge coupling, Casimir of the trivial rep, times the area of the region which is just the area of our spacetime minus the area taken up by this loop. Okay. And when you just multiply this all out with the correct 1/n normalization from the Wilson loop, you find that it's e to the minus g squared times the Casimir, which is n/2 at large N times the area of the loop. So this is area law. This is probably the simplest calculation that rigorously gives you area law with no approximations. And so, yeah, this is very nice. And it's telling us that even though in 2D Yang-Mills doesn't have any, dynamical degrees of freedom, gluons don't have any propagating degrees of freedom, this is still a confining theory. Okay, so there's a string tension.
C is the outer contour.
C is the
Oh,
Wilson.
okay,
Yeah.
okay.
This outer contour is like very large,
Okay.
going up to infinity. Yeah. Okay, so we have a confining theory. Now we can incorporate effects of dynamical charge matter. So in the hopping expansion, we start to sum over hopping loops, and at leading order, we consider, the smallest size hopping loop, which is just a single plaquette, and then we could consider 2 of them, 3 of them, and so on. These types of effects will exponentiate to give corrections to the area law contribution. Okay, but then somewhere very far down in the hopping expansion, at an order which is equal to the size or the perimeter of the Wilson loop, we have a contribution where the hopping loop just completely cancels the original Wilson loop. So it's sometimes called the screening loop, and plus fluctuations of that screening loop. Okay, this series will generate a qualitatively different type of behavior, which is perimeter law. So the first types of contributions will just give 1/n corrections to the Yang-Mills string tension. But then we have all of these other perimeter law contributions, but they actually show up all multiplying 1/n. So in the large N limit, keeping the size of this contour fixed, the perimeter law terms go to 0, the corrections of the string tension go to 0, and we just have the pure Yang-Mills area law.
Mm-hmm.
Yeah, so that's the standard quark loop suppression. But now we want to look at these symmetry operators. So as I mentioned before, on the lattice, we can realize these symmetry generators in terms of operators called center vortices. And similarly to the simple scalar field theory on the lattice that I presented, this center vortex is some kind of defect where you modify the action in some way. So remember that we're talking about one-form symmetries. These are symmetries which are generated by codimension 2 operators. We're in 2 dimensions, so we are looking at local operators, and they live on the dual lattice. And the prescription for this operator is that when you insert it, it modifies the Yang-Mills action on the plaquette, which surrounds the point on the dual lattice, by twisting it by just the Zn phase. So that's the center vortex. And it's topological because the same reason as before, you can do field redefinitions to move this phase from one plaquette to the other by just redefining your link variables. So in this example, I have this plaquette, U1, U2, U3 dagger, U4 dagger. And if I redefine the U2 link variable, it moves the defect from this site to this site, and it's topological. Okay, and then just a fact about these operators is that on R2, they have unit expectation value in pure Yang-Mills. Okay, so now we can look at the behavior of these operators in the hopping expansion. Now here I'm being a little bit more explicit. There's a numerator and a denominator. Again, we just look at the leading order contributions coming from a single plaquette. The plaquette could be somewhere outside that doesn't encircle the defect, or it could be right on top of the defect. And then we would have 2 plaquette terms and so on. And the denominator starts with just the single plaquette, which you could put any place on your plane.
A is the area of one plaquette?
Sorry, A is the area of the 2D space-time, which I'm going to take to infinity at the end. Yeah.
Okay, I see. So you have A-1 because,
Yeah, this plaquette can, if it doesn't enclose the defect, then there are A-1 positions,
okay. I
plus
see.
the one where it's on top,
Right,
and
right,
so on.
okay.
So yeah, and then I re-expand the denominator, that will cancel the A-dependent parts,
Mhm.
and so on. So the key feature to look at these numerical, these factors aren't really important. The important part is that when you bring down one of these plaquettes, they scale like n, because you take the trace of this one plaquette. So all of these terms scale like n, and so when you multiply things out, the leading order and the hopping expansion, you already find something which scales like n.
Oh.
Okay. Now, it depends on what you do with k, but this matches exactly with the more general analysis. So if k is of order 1, you can expand this, and you get 1 over n squared. And so this actually does go to 0 at large n, but that's not the interesting case. The interesting case is when k is of order n, where this is order 1, and this small leading order contribution is already order n.
Right.
Okay, so what that means really is that it's not enough to work to leading order. We should also, we should resum all of these contributions. So if we imagine resumming not one plaquette, but 2 plaquettes and 3 and so on, this will build up some exponential, but where now some exponential of minus the hopping parameter to some power times n. Okay. And now we can take the large n limit. This is something which we can take the large n limit of. Okay, so for k of order 1, we have e to the minus 1 over n, which is going to 1 at large n. And that matches with the fact that it's essentially the trivial operator. If k scales like root n, then this quantity is just some non-generic, non-universal number between 0 and 1. But that's, again, inconsistent with the result from ZN fusion rules, which tells you that these things have to have their roots of unity. And then if k is of order n, which is the most interesting case, these expectation values actually just go to 0, exponentially fast with n. So that indicates that the large n limit is not really smooth for these operators. So yeah, we just wanted to verify in a very explicit way that these sort of general arguments about fork loop non-suppression are really true. And this is telling us that there's no emergent ZN one-form symmetry in this theory.
What do you mean by not a smooth large n limit?
Just that it's
not
going to 0 faster than any power.
right.
So it's, yeah.
That's
what I mean.
Okay.
Yeah. Okay, so let me just wrap up and conclude. So this puts us in sort of an uncomfortable situation, because on the one hand, this notion of one-form symmetry is incredibly useful. It sort of revolutionized our understanding of confinement. But in the one situation where we expect, that we have a nice theory with fundamental matter that is nonetheless confining, the symmetry is just absent. Okay. So there's a question of whether there's some generalized symmetry principle that hasn't been discovered yet that could explain the selection rules in large N QCD and sort of recover this connection between symmetry and confinement. But it would really require something new. So we've thought about various things like intertwining one-form symmetry with flavor symmetries, but those types of ideas really only work when you have multiple flavors, and everything I talked about was just for one flavor. So maybe it's something generally new. The general sort of arguments that we gave in the paper also apply to other situations where you have enhanced global symmetries. And actually, they all involve large N limits. So large N Yang-Mills, pure Yang-Mills, also has selection rules that go beyond the ZN one-form symmetry that are not explained by any known symmetry. And our obstructions also apply there. And there are also sort of some proposals for emergent symmetries and two index theories at large N from some orientifold equivalence. Actually, the notion of emergent center symmetry was explored by these authors in this context, but that was sort of before the modern understanding of one-form symmetry. And then there's a question of whether this all is specific to large N gauge theories, or if there are other examples where, as you take some parameter limit, you expect enhancement of symmetry, but there are certain obstructions. So far, we've only been able to come up with large N examples. And there might be some reason, deep reason why that's the case. So Larry Yaffe pointed out to us that, so as I mentioned, the large N limit is some kind of classical limit. And even when you have exact symmetries in a large N gauge theory, the symmetry operators are not included in the set of classical operators. So the reason is just that the classical operators are defined by their property that they factorize at large N, but symmetry operators by definition don't factorize because they multiply things by phases. So even when you have exact symmetries in large N limits, those symmetry operators are not, strictly speaking, part of this nice classical description. So once that symmetry is not exact, it might be too much to ask for that they actually survive. Right. Okay, so yeah, that's all I wanted to say. So thanks, and to answer more questions.
When you say there are selection rules that you wanted to explain using these symmetries, you give them one example
of the selection rule?
Yes.
Okay, perfect. So let's look at the adjoint Wilson loop expectation value.
Yes.
This is neutral under one-form symmetry, under the Zn one-form symmetry, because its anality is 0.
Yeah.
But at large N, using large N factorization, you can write this as, first we can write it as the product of fundamental and anti-fundamental at large N.
Right.
Trivial as one of our express. But then we can use large N factorization. So this is the mod of the fundamental Wilson loop, but that has area law. So this is now twice the fundamental string tension,
right?
And it has area law. So, and similarly, if you look at the adjoint polycop loop at large N, you'd expect it to go to 0.
Okay, so by selection rules, you mean that you can just use large N factorization to show that these go to 0. But there's no way to argue from symmetry.
Yeah, exactly. Yeah.
Okay.
Yeah. So this is actually this was the motivating example that got us started on this. And we thought that, so in 2 dimensions, there's much more than just a Zn one-form symmetry in Pierre-Yang-Mills. There's a whole non-invertible symmetry. And we thought that that non-invertible symmetry is at work here at large N. But these same considerations tell us that there can't be such a symmetry.
Okay.
Other questions?
Not in chat?
Oh.
Okay.
Yeah. So thank you very much for your interesting.
Thanks.